Spherical. One of the interesting things that we actually see with our spherical mirrors are what's known as a spherical aberration. We typically don't use spherical mirrors in the real world. They work well in our physics class in terms of doing calculations, which we'll see coming up shortly. But in terms of the actual real world, spherical mirrors stink. And the reason being is light rays that are pretty close to the principal axis are going to strike the mirror, and then they're going to pass nicely through the focal point. But light rays that are very far off on the edge, we've been saying that they're passing through the focal point, but in real life, that's a lie. In real life, as we clearly see, this strikes here, and it like winds up back here, which means that our image is going to be really blurry. And we don't like blurry images whenever we're doing photography or looking at stars. I want something nice and crisp. So instead of using spheres, we'll actually use parabolas. Parabolas, whenever we kind of cut them out like this, they do a much better job of removing the spherical aberration and focusing all of our light at the one focal point for it. The only issue with parabolas for a class like this is the math gets much harder. The math gets much harder in order to set these up. So we are just going to pretend that we have perfect spherical mirrors. And you can actually see this to an extent. If we go into here, here's our little ray diagram thing. This is a convex mirror. So notice that all the light on this side with our point source, so here's our point source of light moving around here. Our point source, all the light's hitting and then diverging on the right. These orange lines are the virtual images. These are like behind the mirror in darkness. But if you notice this here, notice how we don't really have a point at which the light is meeting. It's kind of like a splotchy mess. And if we kind of move this off-centered as well, it's just like a splotchy mess there. That's because of the spherical aberration. So we really don't like spherical aberrations in the real world scenarios. So we tend not to use spherical mirrors. We'll use parabolas instead. They work much better. As we're going to see later on, when we start talking about thin lenses, lenses act very similarly to mirrors. And we get a similar issue with lenses as we do to mirrors. Just recently, 2019, Rafael Gonzalez from Mexico Tecnológico de Monterrey, he was working on geometric optics, and he was trying to figure out, is there a way to remove some of these aberrations that we get for lenses? And he actually created, mathematically created a lens that looks, really weird. It looks like this blue thing here. But if you build a lens like this, you can remove like 99% of the aberrations that you'd get out of a traditional lens. That's a really important thing because, forever it's just a feature of the lens itself. But with just a little bit of math, we can remove all of this. And this isn't a little bit of math, children. This is an insane amount of math here. But if you think about that, we've been using lenses and mirrors for 400, 500 years now. About 400 years. It was only, at 2019 that we figured out a way to really remove some of these aberration effects due to lenses and mirrors by using these really, really interesting geometric shapes. So all this stuff it's still like on the forefront of tech, and doing like interesting stuff to remove these type of aberrations is always something that we're interested in. Not only do we have these spherical aberrations, there's actually something known as a chromatic aberration, which is that different wavelengths of light will actually strike and reflect off of a mirror differently. So if you want to look at a red image or a blue image, they're going to have different focal points. They'll be in a different spot. So that's something that people have to think about. And one of the really cool things that astronomers have done in the past 10, 20 years is they've started to develop something known as adaptive optics. And adaptive optics is basically, if we have a mirror here, the light's going to hit it in a bunch of funny ways, but what we're going to put is underneath it, we're going to put a bunch of pistons. And what these pistons will do is if we shine out like a calibration source, such as a laser, we'll be like, activate the laser. We'll get this laser to bounce back off of something, and when it bounces back, these pistons will actually slightly bend the mirror. They'll start to push and pull the mirror so that the mirror's shape will change in real time. And by changing the mirror's shape in real time, you can actually remove some of the weird effects that are occurring, because remember, these mirrors, as we've been drawing them in a vacuum. The light is actually passing through, for something like a star, it's actually passing through the atmosphere. And that atmosphere is causing the light to bend and do all sorts of weird things. So we have to correct for it at the mirror itself. And by using all these pistons and doing these very, very quickly, we're actually able to do that. And so adaptive optics is another thing astronomers have been using recently in order to kind of make the best images that they can see.